I want you to think back just for a second to when you were in middle school science class.
Oh, boy.
Right. You're sitting there at your desk, you've got this worksheet in front of you, and well, you're essentially just waiting for the teacher to tell you the right answer so you can write it down.
Yeah, the classic waiting game. Just kind of biding your time until the bell rings.
Exactly. And research actually suggests that in a standard traditional classroom setup, about 80% of the students aren't really thinking.
Wow, 80%.
Yeah, 80%. I mean, they aren't necessarily, throwing paper airplanes or acting out. They're just faking it, slacking, stalling, or just mimicking the procedures without understanding them.
Right, going through the motions.
So today's deep dive is all about destroying that illusion of compliance. We're looking at a framework called Building Thinking Classrooms.
Often called BTC in the education world.
Right, BTC. And specifically, we are exploring how this framework is adapted for a 7th grade life science curriculum called Bioforge. So our mission today, pulling from the Bioforge curriculum guides and cognitive research, is to figure out how we can transform these passive, waiting rooms into environments where scientific thinking is a visible, highly active process.
Because ultimately, science isn't just a list of vocabulary words to memorize, right?
No, definitely not.
It's a verb. It's something you actively do. It's the process of modeling phenomena, arguing over evidence, revising your ideas. And to get adolescents to actually do that, you can't just hand them a shiny new textbook.
Right, that doesn't fix the core issue.
Exactly. You have to aggressively disrupt the physical and the social architecture of the room to actually change the neurobiology of how these kids learn.
Okay, so let's start right there with the problem itself. Because if 80% of students are actively avoiding thinking, we really have to look at the environment that's manufacturing that behavior.
For sure.
The Bioforge sources call this the illusion of procedural compliance, which I think is a fascinating term.
It really is. It's this idea that students are treating a science lab like a baking recipe.
Just following the steps?
Right. They mechanically follow the instructions. Measure the liquid, heat the beaker, record the number on line 4, but they have absolutely no idea what the underlying biological principles are.
It's like a compliance factory. The product they're manufacturing isn't actual knowledge, it's just a finished worksheet.
Yes. And to understand why they do this, we have to look at the brain of a 7th grader.
Which is a scary place to look.
It's a very unique time. The adolescent brain is profoundly wired for social connection, and it is hypersensitive to status. So when you put them in traditional rows, all facing the front, you're actually creating isolation.
Huh. Even though they're all in the same room.
Exactly. And you're enforcing these rigid status hierarchies. Within the first week, students know exactly who the smart kid in science is and who the struggling kid is.
Right. And I mean, for a 12-year-old, looking foolish in front of your peers is like an existential threat.
Totally.
So if you're wired to be social and you feel like you aren't that smart kid, aren't you just going to copy the smart kid to survive the social pressure?
100%.
Yeah.
And there's a literal chemical reality to that threat. When students rely too heavily on teacher approval or they feel that social vulnerability, their cortisol levels spike.
Cortisol, so that's the stress hormone.
Right. And high cortisol physically suppresses the prefrontal cortex. That's the part of the brain responsible for executive function, complex reasoning, and taking intellectual risks.
So they literally biologically cannot think as well.
Exactly. It leads to cognitive rigidity and avoidance. So to get them to actually think, to engage in scientific sense-making, you have to change the physical environment to boost dopamine and oxytocin instead. You have to make it psychologically safe to fail.
Okay, but as a former middle schooler myself, if you just throw me into a group and say, make mistakes, that sounds like a nightmare.
Oh, sure. Group work has a terrible reputation.
Right. The classic trap where the high-achieving kid ends up doing all the heavy lifting and everyone else just coasts. How does this framework actually prevent that?
Well, this is where Bioforge brings in two major pillars from the Building Thinking Classrooms model. First, visibly random groups, and second, vertical non-permanent surfaces.
Let's break those down. Visibly random groups. So the teacher is actively showing them it's random.
Yes. They might use a deck of playing cards or a digital generator on the smartboard to group students in threes. And it has to be entirely visible.
Why is the visibility so important?
Because the students need to trust that the teacher didn't secretly engineer the groups based on, reading levels or who talks too much.
Ah, I see. So it immediately dissolves those fixed social identities. You aren't permanently labeled the slacker or the genius. You're just a scientist working with a new team today.
Exactly. And they randomize frequently, sometimes every single class period.
Wow, every day. That's a lot of movement. But wait, even in a random group of 3, what stops one really confident kid from just taking over?
That's where the second pillar comes in, changing the physical posture of the group. Students actually have to leave their desks and go stand at whiteboards or windows around the perimeter of the room.
Vertical non-permanent surfaces.
Right. Standing physically prevents anonymity. You can't just slouch down in your chair and hide when you're standing shoulder to shoulder with your group at a wall.
That makes a lot of sense. You're forced to be present.
And the surface itself is erasable, which lowers what educators call the affective filter.
The affective filter, meaning like their emotional barrier to learning.
Right. Think about it. When a student writes in ink on a worksheet, the brain perceives it as permanent. A mistake is immortalized.
Oh, wow.
But when you write on a whiteboard, the risk is incredibly low. If you mess up, you just wipe it away with your sleeve. It encourages rough draft thinking.
And Bioforge adds this brilliant constraint to this setup, right? The one marker rule.
Yes. The one marker rule is fantastic.
Each group of 3 only gets a single dry erase marker.
Right.
So you can't just divide and conquer the work. Like, I'll do questions 1 and 2, you do 3 and 4.
Exactly. The person holding the marker is just the scribe. They aren't actually allowed to write down their own idea until the group has debated it and reached a consensus.
So it forces them to talk to each other. Can we anchor this in a concrete life science example?
Sure. So imagine the class is investigating a medical mystery. A patient whose body isn't absorbing nutrients properly.
Okay.
Instead of sitting at desks filling out a diagram of a cell, the random group stands at their whiteboard with their one marker. And they have to draw a model of how a dialysis tube in a physical lab they just did acts like a small intestine.
Okay, so they're visualizing the biology.
Right. They're mapping out how certain small molecules, like glucose, pass through the membrane, while larger starch molecules don't. They have to draw, argue, erase, redraw, really connecting the structure of that membrane to its function.
But what if they get stuck? If I'm standing at a wall with my group and we just can't figure out why the starch isn't passing through, aren't we just going to stand there in frustration?
Well, because all the groups are working vertically around the room, the thinking is entirely public. So if you hit a wall, you engage in what's called knowledge mobility.
Knowledge mobility, meaning look around the room.
Exactly. The teacher encourages them to literally turn their heads, look at a neighboring group's whiteboard, and borrow an idea to get unstuck.
So it reframes looking at someone else's paper. It's not cheating anymore.
Right. It's cross-pollinating ideas. It's exactly what real scientists do. And because the groups are randomized so often, the social friction of doing this wears down fast. Everyone realizes they're going to eventually work with everyone else, so there's a baseline expectation that everyone can contribute.
Okay, but if the students are all standing at the walls arguing about dialysis tubes, what is the teacher doing? The teacher can't just stand at the front and lecture anymore.
No, the teacher's role completely shifts. They move from delivering answers to managing the cognitive load of the room. They're coaching what the Bioforge framework calls the productive struggle.
Productive struggle. And for you listening, I really want to emphasize what this means. Giving students the room to grapple with phenomena, to struggle productively, does not mean just throwing a complex problem at them and leaving them confused or unsupported.
Right, absolutely not. It's highly supported. And a lot of that support comes from how the teacher categorizes and responds to questions.
Tell me about the question categories because this is super practical.
So the framework identifies 3 types of student questions. First, you have proximity questions.
Let me guess, they only ask because the teacher happens to be walking by.
Exactly. Hey, you're here, look at this. Then you have stop thinking questions.
Stop thinking.
Yeah, these are the classic, is this right or is this what you want? Questions.
They're looking for validation so they can just stop working.
Yes. It's a lingering ghost to that compliance factor we talked about. They want to be done. And finally, you have keep thinking questions, which are genuine requests for clarification that help the group advance their model.
So how does the teacher respond to a stop thinking question? If a kid asks, is our drawing of the intestine right? What do they do?
The cardinal rule is that the teacher never directly answers a stop thinking question.
Never.
Never. because giving the answer instantly kills the cognitive work.
Yeah.
Instead, they respond with a guiding question. They might say, well, what does your data from the dialysis lab show?
Right. They put the heavy lifting back on the students.
Exactly. They use Bioforge's habits of mind prompts or specific talk moves like revoicing.
Revoicing, like repeating what they said.
Sort of. The teacher might say, so I hear your group arguing that the starch molecules are too big. How does that explain the patient's symptoms? It's validating their thought process while pushing them to the next step.
It's basically like a personal trainer at the gym.
Oh, that's a great analogy.
Right. Because a trainer doesn't lift the weights for you when you start struggling. If they did, you wouldn't build any muscle.
Right.
But they do stand there and spot you so you don't drop the barbell on yourself. They keep the struggle productive instead of dangerous.
Yes, and sometimes the teacher deliberately adds heavier weights to the bar. Bioforge calls this the problematizing routine.
Adding friction on purpose.
Exactly. When the teacher notices the class is getting a little too comfortable with their current explanation, they intentionally introduce contradictory data.
Do you have an example of that?
Sure, let's say they're studying matter and energy movement. The kids might be comparing a physical lab, like yeast respiration in a test tube, with a computer simulation of that exact same process.
Okay.
The teacher will highlight a specific anomaly where the physical, real-world data wildly diverges from the clean, perfect computer simulation.
And they don't explain why it's different.
Nope. They use a guiding question to force the kids to evaluate the limitations of their own models. It creates this very authentic, immediate need to know.
Okay, I love this level of guided discovery, but I have to play devil's advocate for a second.
Good way.
If they're constantly just doing rough drafts and looking at other groups' whiteboards to borrow concepts, how do we make sure they eventually get to the actual accurate science? Like, how do you stop misconceptions from spreading?
That is a very valid critique. Pure, unguided discovery learning usually leaves novices totally behind, which is why Bioforge uses a balanced pedagogical stance.
Balanced, meaning they don't just use this framework 100% of the time.
Right, it's used selectively, not rigidly. The group work is always followed by a crucial phase called consolidation.
Consolidation. So this is where the teacher actually teaches.
Yes, direct instruction is still absolutely necessary. It just functions as just-in-time instruction rather than front-loaded instruction.
Oh, I like that,
Right.
just in time. So how does consolidation work in the room?
After the kids have grappled with the data and drawn all their messy organic ideas on the whiteboards, the teacher pulls everyone back together. They do a gallery walk of the different boards, and the teacher leads a consensus-building discussion.
It's almost like letting them wander a maze first, so they build spatial awareness and find all the dead ends. But then at the end of class, the teacher pulls out the master map to make sure everyone actually knows where they are.
That's beautifully put. The teacher formalizes those core ideas, mapping the students' everyday language onto rigorous scientific vocabulary. And to ensure the accuracy sticks, the class builds a summary table together on the classroom wall.
A summary table.
Yeah, it's a living public record. They literally lock in their agreed-upon mechanisms and evidence so they have a reliable reference point moving forward.
Okay, so that handles the collective accuracy of the class. But what about individual accountability? Because I could definitely ride the coattails of my group's consensus if I didn't actually get it.
All right, you can't hide in the group forever. After the collaborative work, every student has to transition to independent reflection using a framework called CER.
CER, claim, evidence, reasoning.
Exactly. And this is vital because a middle schooler's brain is naturally prone to leaping straight to a conclusion without backing it up. CER forces them to slow down.
How does that look in practice?
Well, let's say the groups were interpreting population data to understand ecosystem changes. Because Bioforge is adapted for Alaskan contexts, they use a lot of local phenomena.
Right.
So they might be analyzing the causes behind the collapse of subsistence fishing on the Yukon River and comparing that to the high sport fishing yields on the Kenai River.
Okay, really quickly, and just a note for you listening. Obviously, local issues like fishery management can be incredibly politically charged.
Oh, definitely.
So to be crystal clear, we are simply exploring the source material here. Neither of us is taking a stance or endorsing any political viewpoints about Alaskan fisheries. We are just looking at how the curriculum navigates it.
And that's exactly how the curriculum handles it, too, as a neutral facilitator. It incorporates both Western empirical data and indigenous traditional ecological knowledge to anchor these phenomena. But the science classroom is strictly a space for evidence-based modeling.
So the teacher isn't telling them what policy is right.
Never. The goal is simply to teach them how to evaluate complex, conflicting data sets.
Got it. Okay, back to the CER framework. So the group argues over this messy river data on the whiteboards. Then what?
Then the individual student sits down alone, and they have to write their own CER argument in their notebook or digital portfolio. They state a clear claim about why the ecosystem changed. Then they filter through the noise to select specific data points as their evidence.
And the R, the reasoning.
That's where the heaviest lifting happens. They have to write the logical reasoning that bridges their evidence to their claim, like applying the principles of natural selection to explain the data. This forces the synthesis of all those isolated facts, and it gives the teacher a clear metric of individual mastery.
It's so structured. But I do have to ask about logistics. Moving 37th graders around a room, standing up, arguing, managing lab materials. It sounds a bit chaotic.
It can be, which is why the environment has to be meticulously engineered for physical safety and cognitive accessibility.
Physical safety like tripping hazards.
Exactly. Bioforge emphasizes strict material management routines, like using stackable cafeteria trays for each group's lab supplies, just to mitigate the physical chaos.
Okay, but what about the cognitive side? If you have neurodivergent students in the room, I'd assume a loud, high-movement environment might just be completely overwhelming for them.
You'd think so, but the opposite is often true.
Ugly.
Yeah. Take students with ADHD, for example. Sitting still in a rigid row for 50 minutes requires massive amounts of executive function just to regulate their bodies.
Oh, I never thought of it that way.
Right. So standing up and moving between groups actually provides a necessary kinesthetic outlet. It frees up their cognitive capacity so they can actually focus on the science.
That makes total sense.
And for students with high anxiety or perfectionism, remember the erasable whiteboards. That non-permanent surface drastically lowers the stakes of participating.
Right, they aren't paralyzed by making a permanent mistake.
Exactly. And Bioforge takes this even further by embedding Universal Design for Learning, or UDL, right into the curriculum.
UDL, that's about proactively designing the instruction so you don't have to scramble to make accommodations later,
Yeah.
right?
It provides multiple routes into the learning. A great example of this is how they reduce unnecessary cognitive load using AI tools, like DIFIT.
DIFIT, how does that work?
Well, imagine you have a student who is a struggling reader, or maybe they are a multilingual learner. If you hand them a dense scientific article, trying to decode the words might consume 80% of their working memory.
Leaving almost nothing for the actual science.
Exactly. DIFIT is an AI tool that adjusts the lexical density of the text. It lowers the reading level of the vocabulary without stripping away the complex scientific mechanisms.
So it isolates the variable. You're trying to test their understanding of biology, not their reading comprehension.
Yes, by lowering the language barrier, those students are no longer blocked from participating in that high-level debate at the whiteboard.
That is incredible.
UDL also dictates how students express what they've learned. So, say the class is developing an engineering solution to reduce plastic waste in the school.
Okay.
Instead of forcing everyone to write a standard 5-paragraph essay to prove they understand it, the curriculum uses choice boards.
So they get to pick how they present it.
Right. A student could demonstrate mastery through a visual model or a written argument or even a recorded audio presentation. It ensures equitable participation regardless of their background or communication style.
Okay, let's kind of zoom out and look at the whole transformation here, because it's huge.
It really is a paradigm shift.
We started with this passive, stressed-out student sitting in a row, their prefrontal cortex totally suppressed by the fear of looking dumb, just waiting for a worksheet to give them the answer. But by shifting the physical and social architecture, we turn them into an active scientist. They're standing up, they're collaborating with random peers, arguing over raw data, refining models, and then cementing all of that individually through evidence and reasoning.
The environment is deliberately architected to make scientific thinking the path of least resistance. The teacher is still absolutely essential, but their expertise is applied differently. They manage cognitive load, they spot the kids who are struggling, and they provide that master map during consolidation.
It's highly structured, supported autonomy.
Perfectly so.
It is the exact opposite of a compliance factory. And, looking at it like this, it leaves me with this really fascinating implication.
What's that?
If this framework can so radically transform how adolescents process information and handle risk, imagine its application beyond a 7th grade classroom. Think about modern corporate office design or how adult R&D teams operate.
Oh, absolutely. Think about it. How much of adult professional life is trapped in a corporate version of procedural compliance?
Most of it, honestly.
Right. Sitting in isolated cubicles, navigating these rigid status hierarchies, and essentially just waiting in a static meeting for the boss to provide the right answer.
Exactly. What would happen to corporate innovation if companies just dismantled the cubicles, randomized the project teams every week, and gave their employees nothing but a blank wall, one marker, and the psychological safety to actually make a visible mistake?
It's a pretty wild thought experiment.
It really is. It's something for you listening to think about the next time you find yourself just staring at a metaphorical worksheet at your job, waiting for the answer. Maybe it's time to stand up and go find a whiteboard.
I couldn't agree more.
Thanks for joining us on this deep dive into building thinking classrooms. We'll catch you next time.